Hi, you guys. Well, we're back to doing another video of the next two sections of Chapter 18, which is Section 4 and 5. These two sections are focused on the thermodynamics of these electrochemical reactions. When we think of thermodynamics, we think of spontaneity and how entropy and Gibbs free energy plays a role in a reaction occurring. In this chapter, we're focusing on how entropy and Gibbs free energy plays a role in the electrochemical reactions occurring. So let's go ahead and get started. Section 18.4 is thermodynamics of redox reactions. So there's going to be a lot of formula fun and looking at how these formulas that represent relationships interact with each other and can be rearranged to form new formulas that tell different stories. So if you recall, Gibbs free energy is G, and Gibbs free energy has to do with the amount of work that can be done by a system. So remember that this E of cell, which is the electromotive force of a paired cell, is the work that can be done because electrons are going to be running through a wire. And since they're running through a wire, they are able to do work if you put them through a device like a light bulb or a music player or anything that can run off of electricity. So this delta G equals minus NFE. That F is Faraday's constant, which is the number of coulombs per mole of electron, which is 96,500. The E of the cell is whatever E of cell you are doing, whatever pair you happen to put together from table 18.1, and is the number of moles of electrons transferred. I'm forgetting to underline things as I talk. So anyway, now this little knot here, this knot was a little confusing, I thought, in the last chapter. That knot means it's standard state conditions. So let's just continue on here with this slide and look at all these different values. N again is number of moles of electrons. F is Faraday's constant, which is the amount of work that can be done by 1 mole of electrons as it runs through a circuit. And that's in coulombs per mole of electrons transferred. Now, if you remember from chapter 17, we came upon this relationship, and this relationship is the Gibbs free energy of how it's related to an equilibrium constant. And remember, if Gibbs free energy was a large negative number, that meant that it was spontaneous in the forward direction, and that you would have a large equilibrium constant because it was favoring products. Now, since these two are both equal to Gibbs free energy, they can be set equal to each other. Now, like I said, this is going to be a lot of formula fun, and then a new formula that is going to describe the relationship between E of cell and the equilibrium constant as a function of the number of electrons transferred and Faraday's constant. So with a little bit of rearranging, you can see that E of cell is equal to RT over NF ln of K. Put in all those constants, cancel all the units as they would cancel, and you're going to end up with an equation like this. This E of cell then, for any two half cells you decide to put together, is going to equal the 0.257 volts, which is a conglomeration of all those constants over the number of moles of electrons transferred. If you prefer logs instead of ln's, this is another equation that illustrates the same thing as this one. Okay, so that's the difference between those two. Now again, thermodynamics, what does that mean? Thermodynamics means the interrelationship of energy and how they convert one to another. So this little triangle is illustrating that the Gibbs free energy is both related to the equilibrium constant and to this E of cell. Now if you have a spontaneous E of cell, which is positive, you will have a negative delta G, which is spontaneous, which will give you a large K, which means it favors the products. So you can look at that and how those are related to each other as far as spontaneity and products versus reactants being preferred. This table in your textbook just gives you an idea of that relationship, just speaking of on the previous slide. If you have a large negative G, spontaneous, large K, and a positive E of cell, meaning spontaneous and products. That's exactly what I just said on the previous slide. It's just summing it up here in a table from your textbook. So let's do an example. It looks a lot like the example in your fun sheet. This is practice 18.4. So if you look at this equation, you might think, oh, this is a spontaneous reaction. Or is it? I don't know. Think of your chemistry. Does silver really want to be silver metal? Or would iron rather be silver metal? Iron would rather be silver metal. Iron would iron rather be iron metal? It depends on your activity series of metals that we learned about in chapter 4. But either way, let's use this information as far as this equation that we just derived to determine what chemical reaction this equation is going to lean towards based upon its E of cell. So you can go to table 18.1 and get the half reactions for both of these. Now, how do I know who's oxidation and who's reduction? I know that from the balanced chemical reaction. Iron is going from iron 2 to iron metal. That is a reduction. Silver is going from silver metal to silver positive. That is an oxidation, and that's why they're labeled as such. Looking at your electrons, they are equal, so we don't have to multiply either half reaction by a factor. Now we just decide who's the cathode and the anode. The cathode is always the reduction. The anode is always the oxidation. And so we just put in our numbers in from table 18.1, and we get a negative number. Negative means non-spontaneous. So we should expect our K to be very small, which it is. So see if you can get those same answers when you plug that into your fun sheet. But that's how you would do any of those types of problems, because what this is asking you is, what is the equilibrium constant telling you, and how does that relate to the EMF of that cell? If this is a non-spontaneous, and you could see this definitely from looking at the table and where these are in relation to each other. Let's do another example. If we have a balanced electrochemical equation, what is the standard free energy change for this equation? Well, we need our half cell reactions. Once we get our half cell reactions, and how do we know? Gold is being oxidized. That's not good. Calcium is being reduced. That's not good either. This is kind of the reverse of what both of these things would want to do, given their position in the activity series and in that table 18.1. So notice these things are balanced, the 6 electrons and 6 electrons. That would not have come balanced from table 18.1. Now that we put all our things in here, we know that the cathode, calcium is acting as the cathode and gold is acting as the anode. And we get a huge negative number here, not huge, but a pretty big negative number, which indicates non-spontaneous. But what if we wanted to know the Gibbs free energy? Now that we just got that negative 4 point something here that we're going to put right here, a negative times a negative is going to be a positive for this delta G, which would indicate a non-spontaneous reaction, which we already knew because gold does not want to do that. So we put it in and we get a very large positive delta G, which means non-spontaneous. Large positive tells us that the reaction favors the reactants at equilibrium, which we already know. So we would have to say, no, it goes back this way. But now what about concentration? We were just looking at some standard reactions that are always 1 molar in their aqueous solutions. But how would changing the concentration affect things? So let's play some equation fun here again. If you remember this equation from chapter 17, this is at standard state conditions, 25 degrees Celsius or equilibrium. If you remember the bottom of the bowl, figures that we looked at in chapter 17, where we had a bowl that looked like this, and your delta G naught was right at the bottom of the bowl, and that meant equilibrium. I can change this out of equilibrium by changing the concentrations of everybody. So let's keep going here. Now, what did we see here from this chapter? We have delta G equal minus NFE. So what can we do with that? If we know that both of these are equal to delta G, we can set them equal to each other. And you see now this minus NFE without the naught went right here. This guy went right here. We're going to have some fun rearrangements. Now, if this is E and this is E naught, that's what we're putting right in these spots. This looks a lot like that other equation that we just used. Putting in all these constants, we're going to get something that looks a lot like those other ones, except now, instead of E naught on the previous slides, we have this one. E naught was equal to 0.0257 divided by n, ln of q. Oh, but it's not q. Here it was k. So this is out of equilibrium. This is in equilibrium. So at equilibrium, these two things are not equal to each other. They are, this guy goes to 0. So this guy would go to 0. And then you could rearrange this equation, and now Q becomes K because it's reached equilibrium. It's kind of like that bowl thing, because when we had this situation and we pushed it out of equilibrium up to this way, for example, and then we let it go back to equilibrium, it would eventually just sit down there, and this is equal to 0, kind of like delta G. Remember, delta G from our previous chapter would equal 0 here, but not delta G not. That would not equal 0. That was that thing that we could calculate from Appendix 2 from our delta G of formations, and that gave us an indication of where this bowl was. But either way, this is called the Nernst equation. Now you can have it as in the ln form or in the log form, whichever you like, but it gives you the same answer either way. So if we push it out of equilibrium by certain concentration, changing the concentrations of products and reactants, we can alter this, push it out of this to a certain place until it would, run down, and then this guy would equal 0 and it would reach equilibrium. Okay. We have an example problem. We do. So in this example, you've pushed, this is the chemical reaction we're studying, and we pushed it out of equilibrium. I guess if we knew the K for this, we could calculate the equilibrium concentrations, but we're not doing that right now. We're just given certain concentrations, and we want to calculate, we want to determine whether it will occur spontaneously. Well, to determine if something is going to occur spontaneously, let's see what's happening in the chemical reaction. Looks like cadmium is being oxidized, and iron is being reduced. Iron 2 is going to iron metal. The electrons are equal to each other. So now we just have to get the numbers from table 18.1 and plug them into the cathode minus the anode, and we get a negative number. Negative number means non-spontaneous. Non-spontaneous, now this is at 25 degrees Celsius, 1 molar concentrations, but we are not at 1 molar concentrations. This has been changed. So we are now putting in products over reactants. These are products on the top. And this comes from, this comes from this chemical reaction. And then these are the reactants on the bottom. Reactant constant, and remember, solids do not enter into the equilibrium constant or the reaction quotient. So if we put that in, will that cause this reaction to be spontaneous? Well, let's think about it. It looks like products over reactants. It looks like I have a lot more reactants than I do products. I'm thinking it's this quantity here is going to push this thing to become spontaneous or make him positive. Let's see if I'm right. Yes, I am right. This became positive, which means now spontaneous, because you loaded it up with reactants. And E is greater than 0. And spontaneous. Very good. Now concentration, what we just did was changing concentrations of reactants and products, but a concentration cell is slightly different. The two half cells are the same material, but differing ion concentrations. So this is a cell diagram that indicates a zinc-zinc cell, but you have different concentrations. So what do you think is going to happen as far as the movement of electrons? This is kind of like something running downhill. Is something going to become more concentrated or less concentrated as the reaction occurs? What's funny about this is that the oxidation and reduction reaction are exactly the same, but when you add them up, the only thing that's left, because your zincs here cancel and your electrons cancel, the only thing that's left is the zinc ions. But look what's happening. It's going concentrated towards dilute. So now, looking at the Nernst equation, remember this is at equilibrium, is this guy, and this would be 0 because it's the zinc-zinc cell. So now, but we can calculate for this, given our different concentrations of products over reactants. It's always dilute over concentrated. Notice the dilute is the 0.1 molar and the concentrated is the 1 molar. And now if we do those numbers, we get a positive 0.0296. That's a positive number. That is a spontaneous reaction. So it will occur until these concentrations become equal. Because remember, if you have an equal number, it's ln of 1 is 0, and then everything would be 0. So it's like a battery running dead.